Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is period and frequency of sinusoidal waveforms. Our objective is to define period and frequency and learn to evaluate sinusoidal functions with respect to time. This lecture is predicated on the assumption that the viewers watch the sine waves and peak and effective values lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. This lecture presumes the viewer is familiar with radians, degrees, and can convert between these two positional measurement units, has a passing familiarity with the sine function, and can calculate peak, peak-to-peak, and effective magnitudes. Thus far, we've been treating the sine function as if it were a machine that eats angles and spits out values. On an entirely impractical mathematical level, this is true, but for our more practical purposes, sinusoidal phenomena like voltage and current are better thought of in terms of time. As we discussed in the aforementioned lecture, sinusoidal voltage is the result of rotational generators where angular position of the rotor at any specific moment influences output voltage magnitude. Given the rotor of a generator is continually driven in a circular path at a specific rotational speed, one should be able to establish some equivalency between degrees and time. This is pretty easy if you view this in terms of a unit conversion. Several quantities characterize sinusoidal voltage in generators and motors, notably rotational speed, period, and frequency. Rotational speed, symbolized by an N for some unknown reason, is expressed in units of revolutions per minute, or RPM. Consider a generator shaft being driven at 3600 RPM. This means if an observer counted complete revolutions of the shaft for 1 full minute, they would observe 3600 revolutions. Frequency, symbolized by an F, is a related quantity, which expresses the number of revolutions per second in units of hertz, where 1 revolution or 1 cycle per second is 1 hertz. The same generator shaft, driven at 3600 revolutions per minute, would also be driven at a frequency of 3600 revolutions over 60 seconds by means of a unit conversion, or more succinctly, 60 revolutions per second, or 60 hertz. This means if an observer counted complete revolutions of the shaft for only 1 second, they would observe only 60 revolutions. Both rotational speed and frequency are related units, being a number of revolutions or cycles per unit time. It should be noted that a full revolution is 1 full cycle of the voltage waveform, being comprised of both a positive half and a negative half. As we'll learn in later lectures, generators can be driven at different rotational speeds and still output a frequency of 60 Hz if we increase or decrease the number of magnetic poles. However, for this simple example, let's assume a 1-to-1 correspondence, such that 1 full revolution of the generator rotor results in 1 full positive to negative to back again cycle of the voltage waveform. Period, symbolized by a capital T for some unknown reason, in contrast, is the time per single revolution. Given the above generator accomplishes 60 revolutions per second, simply inverting this frequency figure results in a period of 1/60th of a second, or more appropriately, approximately 16.7 milliseconds per revolution. This means every 16.7 milliseconds, an observer would count a single revolution of the shaft. Given frequency is the number of cycles per unit time, and period is the time it takes to complete a single cycle, it can be said that period is the inverse of frequency, and by extension, frequency is the inverse of period. If you increase the frequency, or cycles per second, the period or time per revolution should decrease, and vice versa. Put your understanding of rotational speed, frequency, and period to the test by solving for the following quantities. Again, for the purposes of this introductory lecture, we're assuming rotational speed and frequency have a direct 1-to-1 correspondence. I'll come back to correct this once we discuss generators and motors with more than a single pole pair per phase. By all means, pause the lecture and give this your best shot. If you're tracking, you should have obtained the following values. Given a rotational speed of 1800 RPM, we can perform a unit conversion to show that this is a frequency of 30 Hz. Inverting this frequency, we can find this has a period of approximately 33.3 milliseconds. Given a frequency of 50 Hz, we can perform a unit conversion to show that this is a rotational speed of 3000 RPM. Inverting the frequency, we find this has a period of 20 milliseconds. Finally, given a period of 12 milliseconds, we can invert this to show that this is a frequency of approximately 83.3 Hz. And then perform a unit conversion to demonstrate that this is a rotational speed of 5000 RPM. Note the inverse ratio of frequency and period. As frequency increases, period decreases, and vice versa. What all these differing qualities, rotational speed, frequency, and period, are trying to convey is essentially the same thing. It takes time to travel the full 360 degrees of a circle. What this means with respect to the sine wave is that the output voltage, previously a function of angular position of a generator shaft, can also be expressed as a function of time. Consider a generator with a 50 Hz frequency or 20 millisecond period. Assuming we start at our agreed upon reference in the far right hand side and travel in a counterclockwise direction, it would take 20 milliseconds to travel the full 360 degrees. This is the equivalency we seek. 360 degrees equals 20 milliseconds. Operating under the assumption that vertical alignment of the rotor north to south induces maximum positive voltage, and vertical alignment of the rotor south to north induces maximum negative voltage, we initiate generation at 0 degrees or 0 seconds, where output voltage is 0 because the rotor magnetic poles are equidistant from the stator poles. During the course of one full revolution counterclockwise, voltage would peak out positively at 90 degrees or 5 milliseconds, a quarter of the way into our 20 millisecond period. Let's assume this generator peaks out at 325.3 volts. Continuing our counterclockwise revolution, voltage would again cross 0, going negative at 180 degrees or 10 milliseconds halfway into our 20 millisecond period. As at the start, the rotor magnetic poles are equidistant from the stator poles and output voltage is 0 volts. Continued counterclockwise direction would see the voltage peak out negatively at 270 degrees or 15 milliseconds, essentially 3/4 of the way into a 20 millisecond period. At this time, output voltage would bottom out at negative 325.3 volts. Finally, voltage would hit 0 volts again, going positive, having gone full circle at 360 degrees or 20 milliseconds. If this was a continuous phenomenon, every 20 milliseconds the sine wave would essentially repeat itself, beginning at the 0 crossing going positive. Graphically, period can be calculated as the time between identical points on the sine wave. Given the repetitive nature of sine waves, one can use the time span between 0 crossings going positive, the time span between 0 crossings going negative, the time span between positive peaks, the time span between negative peaks, or any other identifiable point on the sine wave. However, if you use any other point than the 0 crossing going positive, you are doing it wrong. The 0 crossing going positive is immediately recognizable and unmistakable, even by the dimmest of lab partners. In summary, to graphically measure the period, use the 0 crossings going positive. Given we've established that output voltage of a generator is a sinusoidal function dependent upon angle, if we want to know output voltage at specific times, we need to convert between times and angles. Let's say we want to know the output voltage at 2.8 milliseconds. We need to convert 2.8 milliseconds into degrees. Given we're being asked to convert from time to degrees, the conversion factor needs to be set up such that units of time cancel out and units of degrees remain. 2.8 milliseconds times 360 degrees over 20 milliseconds yields an angular position of approximately 50.4 degrees. Substituting this angular position into a sine wave function with a peak value of 325.3 volts yields a value of 325.3 volts times 0.7705, or approximately 250.6 volts. By the way, if you're getting an incorrect value of 43.6 volts, it's because you failed to set up your calculator in degree mode as asked, and it's assuming you mean 50.4 radians. Your calculator must be in degree mode for this to work. Given we can establish some equivalency between degrees and time, we should be able to do this in a single step. The value of this function could be more succinctly represented as 325.3 volts times the sine of 360 times the time of interest divided by the period of 20 milliseconds. Or more generally, the peak value times the sine of 360 times the time of interest over the period. Note the general form is expressing voltage as being dependent upon time rather than angle. The math inside the parentheses simply converts time into angles in units of degrees usable by the sine function. While understandable, this format isn't especially pretty because of the ugly division inside the parentheses. Add to this fact that period isn't an especially common specification. Ordinarily, frequency is used to specify AC voltage. Given there exists an inverse relationship between period and frequency, we can write output voltage as a function of time being equal to the peak value times the sine of 360 times the frequency times the time of interest. For the specific example, the general expression would be V of t is being equal to 325.3 volts times the sine of 360 times 50 times the time of interest. To solve for the output voltage at specific times, simply substitute the time of interest and let the math take you where it may. Using this single-step formula, it can again be demonstrated that output voltage at 2.8 milliseconds is approximately 250.6 volts. Let's say we want to know the output voltage at 3.5 milliseconds. We would substitute 3.5 milliseconds into our voltage as a function of time formula. Performing the unit conversion inside the parentheses first yields 325.3 volts times the sine of 63 degrees. This yields 325.3 volts times 0.8910, or approximately 289.8 volts.